Well, welcome back. This is signal integrity and electromagnetic compliance training for mere mortals. My goal is to teach everyone in the universe how to design high-speed digital analog RF systems that work right and pass FCC and CISPR tests on the first try. I'm Terry Fox, and off we go. So, this segment is going to be about ground bounce or power ground plane noise. So here we go. Ground bounce or power ground plane noise is caused by the impulse current demands of digital switching drivers. If I didn't have these noisy switching signals, I wouldn't have any real problem as far as the power delivery or the power noise. We've always heard that digital power planes are noisy, blah, blah, blah. Well, if you look at something like a memory bus, like let's say DDR2, I could have up to 64 bits going from 1 to 0 or 0 to 1 in under a third of a nanosecond. Okay, now let's kind of put some math behind it. If I had 30 milliamps per bit, 64 of those bits would be almost 2 amps. So if I had 64 bits going all F's to all zeros, all F's to all zeros, what I'm doing is I would be switching on and off approximately 2 amps at an edge rate of about 3 gigahertz. Now, that takes some sort of pretty serious power delivery system to keep something like that quiet. Because it's not just a case of are you delivering enough current, but the question is, are you delivering enough current across the frequency range of interest? Now, noise will increase with a faster edge. So if you make these edges go faster, the noise will increase. It'll also increase with a higher current draw. So if I've got a faster edge or a higher current draw, then the noise increases. Now the noise will decrease with a slower edge or a lower current draw. So if this rise time, instead of being 350 picoseconds, was maybe excuse me, a nanosecond, then this would be a far easier problem. Or if we happen to have a memory circuit where instead of pulling, say, 30 milliamps per driver, if it was only pulling 10 milliamps per driver, that would be less of a problem. Now, noise will also decrease with a more robust power delivery network. So if I could look at the impedance of the power delivery network as a function of frequency, if that impedance was a tenth of an ohm, that would have far less noise than if the impedance was 1 ohm. Okay, the tenth of an ohm impedance between power and ground across a wide frequency range will have significantly less noise than if that impedance between power and ground was, say, an ohm instead of a tenth of an ohm. Now, if you're going to understand power delivery noise, you have to understand what are the pieces in this design. If I start from the power supply or the voltage regulator module, that will supply your volts and amps, and it brings that power to the power plane and the ground plane. And the first thing that we'll see when we get onto the power and ground plane, and this could be a split plane as far as the power plane is concerned, but the first thing we'll see when we get there is going to be the bulk capacitors. These guys are going to be your 100 microfarad sort of capacitors. But as capacitors, you'll find that they've got equivalent series resistance internally. They've got the capacitance which you wanted, but they've also got equivalent series inductance internally. There's also the mounting impedance to the plane on the power side and the mounting impedance to the plane on the ground side. So consequently, these can have fairly significant inductance associated with the 100 microfarads or 300 microfarads or 47 microfarads or whatever these things happen to be. So, but these are connected to the power and ground plane. The next, and if I look at what these will do for me, these will probably take a frequency response that probably gets pretty weak up around, say, 10 kilohertz on the power supply and probably bring it up into the tens of megahertz because of these capacitors. So at DC, the power supply is a low impedance, but as you get up in frequency, someplace between 1 kilohertz and maybe 10 kilohertz, typically the internal inductance in the power supply has got too much of an effect, and these just simply cannot supply the current at higher frequency. When I add in the bulk capacitors, then I'm able to flatten out that frequency response and supply current up to maybe the low tens of megahertz. There are some of these capacitors that are very, very good that might indeed deliver it up to, say, as high as 80 megahertz or 100 megahertz. So there are some pretty good capacitors out there. If you want to learn more about how a capacitor behaves, I highly recommend that you download either the Chemet or the Chemet or AVX SPICE programs. And you can play with capacitors and see how that stuff works. You can go to the bibliography on siemc.com and see the links for getting those SPICE programs. They're just free. Download them off the web. So here I'm good up to maybe 10 kilohertz. Here I'm good up to maybe 80 or 90 megahertz. And then I have to add chip capacitors, and the chip capacitors, these are guys like your 402s and 603s and 805s and things like that. And these capacitors, we typically have quite a few of them on a design. But again, I'm buying capacitance, but along with that capacitance, I get equivalent series resistance that is part of the package itself. I also get equivalent series inductance that is part of the capacitor, plus the mounting capacitance to the power plane and the mounting capacitance to the ground plane. But if I have a reasonable number of these capacitors, I can probably get the impedance down low enough, say up into the 250 megahertz range, maybe 300 megahertz range if you have a lot of these on there. But once you get above about 300 megahertz, it starts taking a rather ludicrous number of chip capacitors in order to hold down the impedance. So the next thing that we look at is we look at the interplane capacitance. That is that if I've got a power plane in parallel with a ground plane, there is capacitance between those two planes. Now, you'll notice that in all of these devices, I showed that there was mounting inductance. And when I show the interplane capacitance, there is indeed some inductance, but it is so much lower than the inductance of even a chip capacitor that it would be misleading for me to show the inductance in this interplane capacitance. And so consequently, this interplane capacitance, as I go higher in frequency, this actually becomes more beneficial until finally we get to the point that the inductance associated with it starts becoming dominant, and at that point you'll find you go higher in frequency and it gets worse. Well, eventually we get over to our active device, and here's our driver, and in that active device there must be some on-die capacitance. There has to be some capacitance that is bypassing this driver. That is because I've still got mounting inductance where the memory chip or the FPGA or the processor is mounted to the printed circuit board. So there has to be some on-die capacitance here. Now, with the exception of the top end Xilinx Vertex and Altera Stratix, whatever it is, they don't tell you what this inductance is. Now, if I don't know what the on-die capacitance is, I don't know how high in frequency I need to have a low impedance as far as these planes are concerned. So we get sort of into a catch-22. If you gave me infinite on-die capacitance, I wouldn't need any of this stuff. All I'd need is just the power supply. Give me a battery and some long wires, and if I've got enough capacitance here, then everything's fine. Now, one clever thing that, Xilinx did, and I'm sure Altera's got an equivalent thing to it, is they actually put, I think it was 47 microfarad Murata chip capacitors inside the ball grid array. Now that's pretty slick because what they're doing is they're getting that capacitance on the chip side or the die side of this mounting inductance, and that is a wonderful thing to do. But for most of us, we are faced with the fact that we don't know what the on-die capacitance is. We need to build something back here that will make it work. And so consequently, you get into a situation of saying, well, all right, if I don't have the information here, I need to have some sort of strategy that makes sure that I do well enough with this stuff to make sure that if this chip works on anybody's board, it works on my board. So that's where we'll go from here. Now, if you don't have enough capacitance between your power and ground planes, for example, here is a 6-layer board where I've got signal, ground, signal, signal, power, signal, and between the ground plane and the power plane, I'm showing a capacitor here and a capacitor here, and then this is an active device connected to the power plane and the ground plane, and then I've got some capacitors on the back side here that are going to the ground plane and the power plane. So this is just a straw man setup that I put together, and here I've got 25 402 0.1 microfarad capacitors, and this up here I think was 16 10 microfarad capacitors, and then the rest of this little example was just showing different places where I had vias, where I had power pins, and of course all of this was done with the Hyperlinks line sim. And so this thing is a 6-inch by 6-inch board. This is one of the labs that we do, and the voltage regulator module is down there, and U 2.1 through 2.9. So 2.1, 2.2, 2.3, 2.4, 5, 6, 7, 8, 9. These were various places where I could pull power out of this. And like I say, this was just a setup in order to do some experiments. But in this particular case, what I was looking at was the noise on the power plane when these things pulled current. Now, when they pulled current, you'll notice that in this area where I have a lot of capacitors, that's that blue area, it tended not to move very much. But in this particular case, it was moving almost half a volt. This area in the blue was moving almost a half a volt. And when I get out to the worst case area, out here in the light yellow, it was actually moving almost 1.2 volts or 1.16 volts. That's how much this voltage was deviating from the norm. So consequently, you can end up with some rather amazing amounts of noise just depending upon how you go put this stuff together. As far as the requirements, you've got DC requirements and then you've got AC requirements, and these AC requirements are determined by the impulse current demands of the I/O drivers. Now, if I look at something like 133 megahertz SDRAM, then if I've got 64 bits at 30 milliamps, that's about almost 2 amps. It's switching at a 350 picosecond rate, and so therefore that's about 3 gigahertz. This is a big deal. That is a huge current requirement. On the other hand, when I look at something like a CPU core, at full power it's about 7 amps. If it's just running the clock chain, it's about 2.5 amps. But once it is operating at any particular level of work, there is lots of random balanced demands inside the core of the chip. It's physically small. It is not routing dependent. The manufacturer tells you how many capacitors you need, and when it ramps from 2.5 amps to 7 amps, it does it over many, many clock cycles. Okay, my apologies. Due to YouTube video length requirements, I have to terminate this thing. You can get the entire thing on SIEMC.com, and thank you very much.